a sec. So we're recording here.
Well, I already knew I would.
Okay, everybody. So we'll get started on day 2. Welcome everybody on a remote session, and welcome everybody at the home session here on site. Still trying to work out some of the AV issues. We've got 200 meg actually. We did not succeed in getting the 1 gig connected, but tomorrow that should come online, so we should have even better. But I think with the 200 meg it was so far. Today we're going to start with a presentation by William Neal. For 15 minutes, just a brief overview of the work he's been doing, starting an OSE club in London, Ontario, Canada, a place called London International Academy. It's a high school level, fully with international students. And we'll talk about our experience there, learning for spreading this to schools and different spreading open source ecology work to different schools, different locations worldwide. He's the first test case of that, we're trying to develop that program. So after that, we'll go into speaking about collaborative literacy. Because we're working on a universal access in a shop, actually building a 3D printer right now, we'll switch the sessions around. So in the afternoon, we'll talk about collaborative literacy. But right now, focus on the universal access build systems. That's a live build in the workshop. So we'll do that in the morning, and then also discuss just a little bit on how, as a team, based on learnings we started yesterday, how to make that process better when we have a lot of novices and some skilled people in the shop. And how do you make that work effectively so we're learning from each other and creating a rapid learning environment for that? So we'll start here. Let's go to William, and we'll start with that. Now, people on a remote session, you can go to this place. I'm pasting a link. Let me reopen. I'm going to paste the link for William's presentation. And is that just a picture? Okay, so he's got pictures. You can follow the pictures. It's got all these pop-ups covering the chat box. Okay. Okay, link to William's presentation pasted in a chat box of Jitsi, so you can click on the bottom left corner to access that. And otherwise, let's have William, my co-instructor in this workshop. Go ahead, William.
So good morning, ladies and gentlemen, remotely. Good morning, ladies and gentlemen, here at the farm. It's a great pleasure to be with you all this morning. In thinking of this presentation, I'm sort of thinking of the individual participating in this workshop. And how can one get involved over the long term in the work of open source ecology? And so I might just give a very brief overview of my own involvement, and then show some pictures of our recent work with Open Source Ecology, with our Open Source Ecology Club that started in Ontario. So when I saw the TED Talk, I went to Factory Farm, of course, and it was an exciting time, and coming home I was really excited by the learning of my son. The one challenge is, how can you build a brick press in your garage? My wife wasn't so hot on the idea of welding. I didn't seem to think it was a problem, but she was not into that. And I actually got very close to getting 3 friends together to, we identified a place, we identified the parts, we had the plan ready, we just didn't execute. Because it would have taken all 4 of us a little bit too far afield from our regular everyday lives and too much strain on our already full plates. So we came very close to actually trying to build the brick press that same August of 2011 in London, Ontario. So at that same time I transitioned to a new job at London International Academy. And so that was a very exciting time to go into a new workplace. And so as a new employee as well, I felt really bad that all the footage I took at Factory Farm, I didn't have the wherewithal to get it up there and document it, because the new job was kind of overwhelming with all the new requirements. So I just came into this school as an international secondary school. The culture, of course, is like almost any other school, rows of desks and all of that.
Okay, hold on. Audio cut out. Let's see. How do we...
Yeah, audio cut out for me too.
Yeah. It's on the microphone mute.
Let's see.
But you can turn off the speaker here. I'll turn off my speaker. There we are. Okay, now is that okay?
Can you guys hear now?
Yeah.
Good to go.
Excellent. Okay, go ahead.
So here's the problem that I faced in education. There's a very strong and pervasive culture of paper and pencil testing, and yet I saw a proof that education is way out to lunch when it comes to actual learning. And so what am I supposed to do? For the first 2 months, I just sort of towed the line. I did a paper and pencil chalk and talk class and talked in front of my class for 50 minutes every day, or an hour and a half every day. And the very polite students all looked very attentive, but of course only 5 out of every 30 of them got anything of value from what I may have been saying. Because whatever I say in a class, most of it is too high or too low for what the typical student is taking in. By chance, a few of them are right at that right level and like to hear and learn that way. So I started a project in April of that same year, and we just had a discussion in class. 3D printing came up, and we ended up building this 3D printer. So I'm just fast forwarding through a few years here. The 3D printer proved extremely exciting for the students, but I could not find a way to map it into the curriculum. It's too top-down, too narrow. So we just started a lunchtime club, built this 3D printer over a few years of lunchtimes, 20 minutes at a time. I used to leave a meeting. I was the vice principal. I would just walk out of a meeting. People wonder where I went. I went to go and hide with the students and build a 3D printer. It's a school. We should focus on education. The paperwork can come later.
Yeah.
And the nonsense can come later, and the politics can come later. And so that was a slight risk on my part, but it really paid off. Because when it worked, the students loved it. They ended up donating their own 3D printer. The reason I chose the 3D printer, it's one of the GBCS 50 machines. So in the last 8 years, I start every class with the 4-minute TED Talk, every STEM camp with the 4-minute TED Talk, because I'd like to start some context that, wait a moment, we don't just have to sit back and watch this like a movie. We can jump in, take action, and do something different and make a change.
GVCS is Global Village Construction Set, for those who don't know.
So there's the... this approach has proven extremely exciting, and my job evolved from a chalk and talk teacher in 2011 to... It's very difficult to describe. When I say I'm a teacher, I don't really think I'm a teacher anymore, because whatever they call a teacher is not what we're doing. So I step back and let my students do a lot of the learning. And other teachers come in and say, well, wow, where did you learn to do that? And I said, for my students. So this is the little slideshow. We're going to fast forward a few years here, and I'll see what we did in the last few months. Marcin and I connected in around October of last year, and I just mentioned to him that pretty much my entire career is now based on the OSE, because that's how we started the class. And then we arranged for him to come up. Him and Katarina came up. They gave a talk, and they engaged our students for a few days in London and challenged them to join an OSE club. So, of course, my job is very busy right now. We have a robotics team, and we're just going into robotics season. But somehow we managed to stick, in the middle of the robotics season, the OSE club context. And I mapped it onto the curriculum of another class. It doesn't work well in physics class, but computer engineering technology, it worked. So here's a little summary. In the middle of the robotics season and the most intense semester of my year, also we had 2 visiting schools. One from Nanjing Jinling High School, one of the premier high schools in Nanjing, China. And so they came in for a 4 or 5 day STEM camp. So we had this concept of starting these STEM clubs all around the world. That's how I like, let your vision be world embracing, not confined to your own self. Let's think about the whole world. So they came in, we said, oh, let's start the OSE club with these students. I had never done FreeCAD before because our robotics teams are all into these proprietary things, and we kind of got locked into SolidWorks. And we got a $12,000 discount, so that's pretty good. We were able to afford it. But with the OSE club, it's just too much to think about using SolidWorks. FreeCAD is where it's at if you want to have global collaboration accessible to all. So my very first experience with FreeCAD, aside from a couple of minutes of dabbling, is this set of students right here. So they came in, we gave the idea, what if we were to make a cordless drill? We talked about that concept yesterday. Well, let's start with a motor. So we had a design of a motor online, and we showed them this video online, this very amazing sort of an open source enthusiast from Germany, Christoph Leimer. It's very good for you to go and check out his work. Highly recommend. It's extremely inspiring how precise, and it's just a beautiful work of art as well as a motor. So we took that video, we watched it, and then the challenge was, okay, design that motor now using FreeCAD. So the way I got it started, there's a little bit of chalk and talk just to get the fire started. So I would go up with the students and we made a circle. We extruded the circle, then we drew on the surface of the circle to extrude up a cylindrical hollow portion, and then we did a cut in one part of it, and then we learned how to do polar cuts. We're going to do all of that during this camp here. So within about an hour, we had enough skills from the typical student to be able to make something that looked like a motor. So here's the Nanjing students. We'll go to the next slide. And here is the result of one of the students, Ge Wen-yi is her name, and she made a prototype. It looks nothing like the motor that we have right now, but it has all the elements. There's a cylindrical shape, it's hollow. She even tried to put the threading on it. We never got around to putting the threads. We just used duct tape. It's pretty good. It's just very satisfying. And there are slots in the motor, and irregular intervals around the circle. So all the elements that we required in the motor were done. And this was only a very few hours. Those students were only in the STEM camp for a very short time. So we're very happy that a few of them got all the way to all the elements of the motor very quickly. So shortly after that, we had visitors from Tiffany's School, School of the Nations. That's the very first school where I started teaching in 1996. From Georgetown, Guyana. Here are three of the students. And here they are also working. We also built a 3D printer with them. They had their own 3D printer. They brought it up and we're fixing it. So we completely rebuilt it while they were there. And they also participated in the Open Source Ecology brushless motor sort of competition. We're envisioning eventually this is a full competition. So the first group of students made a basic shape of the motor. This allowed me to reflect, okay, well, what went well, what didn't go well? I thought about it, and then I tried the same FreeCAD lessons again, and we got further. Ronaldo, one of these students from Guyana, he actually got to the point where we had slots for the magnets in the motor. And also, very short time, they're only there for a few days. We did the OSC as part of a bigger set of events. We did computer programming, robotics, so a very short time on FreeCAD. And we 3D printed out parts that are now starting to look closer to the final product. So we'll go through. Here's the Guyanese team. They're all amazing set of students from Nanjing and from Georgetown. So now, at that point, another unit started in my computer engineering technology class, and that unit was the one that overlapped with motors and motor controllers and the like. So I introduced this as a topic to my students, and one group of students selected it. In my classes, we do not do the same thing. If there are 20 students, there may be 3 or 4 groups who are all working on something different but complementary. But one of the groups selected the motor controller. So this is the first, the motor project. This is the first part that we printed out, and one of my students, Ben, he just took off. It seems that each group had 1 or 2 students that really took off with this one concept. And within a few days, he went from 0 to an extremely close replica of the original motor controller in the video. So down to the fine details. So we'll just take a little look at it. Fit perfectly. The little bearing fit perfectly in there. And here are a few of there's the progression of the parts from the first group from Nanjing, from the Guyanese group, and up to Vincent within a few weeks. So my ability to teach FreeCAD, but also the students' ability sort of changed over time. My students kind of cheated a little, they had more time. So there are some of our sample parts and printouts, and gradually we accumulated more and more parts. Oh, everything was just fitting together. So here we are, going through the process. They eventually got to the point of winding the wire. We took 6 strands of wire on a 5-meter sort of loop around a screwdriver at one end and a screwdriver at the other end to get the wire wound to the strands. And they stretch it between our robot and the vise. I don't know, they just chose 2 arbitrary points 5 feet apart. And there they are, the rolls of wire all ready for winding. There's the wire winding. They did a great job on that. And taped it down so it wouldn't fall off. It's not perfect, but it works pretty well. It's a pretty amazing job for an extremely busy classroom with lots of other things going on. They just did that in the middle of chaos. And once it was done, he taped it all up so it wouldn't fall apart. So that was good. And they were very satisfied. Like you can just see here. Here's one of the interesting things about it. This is why I like the Open Source Ecology project. For me, this is my professional development training. I cannot get this kind of training anywhere else. You cannot get hands-on training that really produces education anywhere else. Please tell me if you found it. I haven't found it. So the metric is, what is the attendance level in a class, and what is the commitment level of the students? First of all, the average attendance level in our class was higher than 100%. For example, she's not even a STEM student. She was our poet in residence. She just came into the class and hung out at any time. She was just interested in the energy and the creativity going on, and she was really happy when they got the motor done. She has no interest at all in STEM, but she does have an interest in their excitement. And so that's one of the metrics. The other is that Vincent spent 4 entire days after he got the report card. He was done high school. He should have been off doing something else. He spent 4 days to complete the motor because he got it to this point in class, but he actually put everything else around it. And he was just excited to see it working.
Did it work? Okay.
Oh, well, I guess we have to see the end of the movie. We're almost at the end here. I think we're probably close to our 15 minutes, aren't we? So we'll just do a fast forward through a few of the things. Here's Vincent's rotor. It's bigger. It's the right size. It has the right number of magnets. We make something called a Hallback array here. The magnets rotate by 90 degrees in polarity. Each magnet. There are thick ones and thin ones. Mr. Leimer's design. It's not completely symmetric, but it seems to work. So we have wide magnets and square-shaped magnets, and each one is rotated 90 degrees in polarity. Here's the motor in the casing, and finally there's the completed motor. So if we take a look over here, we have the motor. Here's the final product. We can pass this around, and you can just put this in the camera if you want.
If people are catching this, let me see. Hold on.
Yeah, it is. It's on there. So.
Yeah.
So just showing it.
Yep. So look at this, guys. This is built 3D printed. Williams class. Pass it around.
And you can see there's a duct tape sort of holder there. Instead of bothering with the threads, which is up to someone else, we just use duct tape. If we want to take it apart, we'll just take the duct tape off. So let's just see. There's some of the parts and the evolution of the motor from January to April. It kind of evolved with 3 different classes from 3 different continents. That was the most satisfying part. Not the fact that we made the motor, but that we're establishing a global network of collaboration in technologies that can make a difference, sharing them, and this could be the start of a process where we make really significant products in a short time. Because this took relatively little effort. Like, if we add up all the time of development, it's very little, because highly distracted, all 3 groups had to do all kinds of other things, and yet this was finished at the end.
Materials cost in the whole building.
So I think the hardware was $100 Canadian, which is a good deal for Americans. It's only 83 American dollars. Yes.
Did you guys measure output or anything like that?
We just qualitatively did that. It spins pretty quickly. I would guess 3,000. Haven't got to that point yet. The students are all graduated, so the only thing I did was turn it on.
Okay.
They didn't get to the point of turning it on. They got it to the point of being ready to turn on. I hooked it up to an ESC and got it up to perhaps 2,000 or 3,000 RPM.
Under what load?
Under very little load.
Very
So
small current,
here,
small voltage.
here's the sort of thing. This is an educational project. It can do a very light loads right now. If we were to adjust the core, we're going to get more.
Got it.
So we have some iron-filled, it's called protopasta. It has iron filings in the PLA filament and can increase the output by about 13%, but a professional grade motor will have an iron core. And the things we were talking about yesterday, iron working, if we were to be able to fabricate our own core, then we're going to get up to the next level. So that's part of the development of the nice goal, if we were to be able to come up with a way of putting an iron core in there. So maybe we could get around it by just taking some iron and 3D printing around it or something, just arbitrary blocks of iron. Yeah, so it'd be amazing to come up with something better. So I commandeered my son's remote control unit and found a way to get it to work with the motor. And maybe we'll just see some footage of it working right here. There it is. There's the motor spinning.
Oh my God.
It's so amazing to have that happening.
Wow.
So student designed, fabricated. It would have been student tested. We ran out of time. Because if I had a school, we would focus on this all day. But in the regular school, we're trained like dogs to obey that bell. Now it's time for English. Get out of this class. So there we are. in my view, this could be the core of a huge amount of learning in a physics, chemistry, science, all kinds of topics can be worked right into this one project. It's called a keystone idea in education. It's all through educational theory. In practice, almost never there, because you've got the SATs, you've got your final exams, you've got your A-levels, whatever it is. Oh, so we don't have time to think laterally. Just get that next problem done, because you want to get a 1400 or whatever on your SAT. I don't even know when you got to get on SAT. We're lucky in Ontario, we don't even have those. So that's one of the things we have that benefit in Ontario. We don't have the final exams. That allows us to do this. But even so, Ontario could improve a far lot by taking away the top-down requirements of the curriculum and letting the people who are involved decide on the things they need to learn. So this makes work into play, and the students love it. It's changed my entire career, and this is why, from my point of view, the Open Source Ecology provides the highest level of STEM teacher training I can imagine. And I would recommend it to any teacher, but also to any other enthusiast. It's just so incredible what we can do in collaboration. So I hope I don't know what time we're
Yeah, okay. William, thank you so much. So, what a great example. That's a great example of practical work. In case, I know there was a couple of cutouts on the video there, but I did get it recorded, so with sound here, so any one of the remote people who missed it, you will get a chance to watch it on a recording, which I will do like right after we're done here. Yesterday I didn't do that. Okay, so let me just make sure I'm on the right screen here. Somehow I'm on William's. William, can we cut you out? You seem to be dominating my desktop.
Oh, sorry. There we go.
I don't know why. I'm not able to switch into my own.
There we go.
Okay, there we go. There we go. Okay, now just to follow up on William's work there, that's one design. It's a particular geometry of a motor, but there's different ways to do it. What he's doing is called a radial design, where the magnetic field kind of goes in towards the radius. There's other ways to do it, like axial, where if that's the shaft, the magnetic field goes along it. It's actually a much easier design to implement. Looks completely different than that, but that's actually, we think, is much easier to build. And actually,
the cordless drill
could be the core of the cordless drill. And why we're interested in is, I mean, the motor is just one of the most fundamental tools in civilization. Like, you got electric motors, you got hydraulic motors, you got engines. But here we have an example of building that from scratch, which when we started maybe a decade ago, it was like, wow, we didn't even think about 3D printing, because at that time it was really not possible. And you do have magnetic filaments where you can print the magnetic core to a decent level. The guy, the originator of this, his efficiency, did he get it up to like 80% right now? Or
he has very high efficiency, but the torque, so he did the protopasta, and it gives you more efficiency, but not a huge amount more torque.
Well,
so that's something that other people have measured, and it's significantly higher, something like 8 to 10 times higher torque if you use an iron core.
Yeah. Now, still with the magnetic PLA, I did see a video following up on that some guys did an aerial vehicle, a real flying unmanned aerial vehicle, basically a plane that uses Christopher Limer's motor. It worked enough to get a plane off the ground, so that's good. Okay, so wrapping that up, and we do have, if there's any time off time, we did bring parts for the other design, the axial type motor.
Yeah, and that could be a project for the last few days if someone wants to design
and
make a motor from scratch. We may have enough time to do that.
Yeah, the bottom line on the axial design is that right now, not using magnetic cores, because with that kind of design, you don't need a magnetic core. It actually doesn't help it because of the way because of its geometry. You can make a pretty efficient thing, and just like with the cordless drill challenge, we are open to people doing either a 3D printed electric motor or just getting one off the shelf. Now, there's advantages and disadvantages to both. I think the technology is there that we can absolutely do a 3D printed and fully open source homemade one that's highly efficient, because there's examples, the one we worked from, It was a tiny little motor. It was 500 watts. Very fast. It was like 8,000 RPM or so. It's on the wiki somewhere. If I'm not going to pull it up right now. Okay, but let's move on to the main topic, which is core to the Steam Camp right now, is the universal access system, which can be scaled and modified and applied to many different CNC machines or any robotics motion system in general. So I'm going to share my screen for remote people. And as far as the local participants, please go to the page on a wiki called Universal Access. So on my computer, I'm going to go to Universal Access. So anyone who wants to follow that, William, would you mind maybe opening up your computer so you can kind of follow where I'm on that?
Sure.
Okay. So people locally can see it. Page on the wiki called Universal CNC Access. So yesterday we have experimented with it, actually building it. And to review the basic design, you have a linear axis with a motor on one side. The carriage is the only thing that moves back and forth on a linear guides. And then there's an idler piece on the other side. It's belt driven. So that's one of the aspects of belts. I mean, they're very low cost. They work for this. They're as strong as the motor that drives them. Typically when people do a 3D printer, they use not belts on the z-axis. Typically it's XY that is belts because they're efficient, lightweight. But on the z-axis, typically people use screws, like ball screws or other precision screw, which from our perspective, OSE is about reducing part count and simplicity. So we're saying, well, how about we just use that for the z-axis as well? And we did exactly that. So we're using the belts on all axes so that if you know how to do one, you know how to do all of them. And that's a great point of simplification for everybody. Now I'm having trouble loading here, but okay, you've got it there. So maybe I'll take a look at that. So let's go to the on a wiki page. Let's go scroll down a little bit and let's just take a look at the diagram in detail of all the parts that a universal axis needs to have. And you need to have that. Keep going down. Just scroll down a little bit. No, maybe go up. Go up a little. Go up. Go up.
There was one.
Yeah,
there was one
I
here.
think it's not loading, but yeah, okay. Grab that one, and let's expand that picture because it shows. I want to go through in detail what each universal axis.
This was a
does
Facebook
have.
post. I bet. If
Yeah.
you
So
showed
what I
them-
do on a wiki is embed. Like it's very convenient to throw pictures up onto Facebook and then embed that stuff in the wiki.
There we are.
So you don't have to do that over and over. Okay, so if you go click on the actual Facebook post there. Okay, so this is an exploded part diagram showing all the different parts. So once again, 3 different part sets. So you've got the motor side, which is made of 2 3D printed pieces. You've got the carriage side, which is made of 2 3D printed pieces. And then there's the idler side, which is made of 2 3D printed pieces. And I mentioned that yesterday that they're all clam, like a clam sandwich, for the purpose of accessibility, and you can add things on the inside of that. So for example, on the motor side and on the idler side, and I'll just point out that this idler here is the long version of the idler. Right now we're using the shorter version because all you need to do is fit a small bearing idler in there and be able to attach it to a frame. We don't need the entire thing, and we shrunk it down to get more space and faster printing time. So, but you can still use that. It works just as well. It takes more space and so forth. You can also, if you go to the wiki and go to the part on the same page, you probably have the part library somewhere, which there's a bigger one here. Okay, so this one here, let's take a look at that. It's actually a little more visible. But this is all in CAD that we have accessible, so you can download all the individual parts. The parts that we 3D print are, yeah, go back. You're basically combining the general concept of 3D printing, which is you've got complex geometries that are achieved by 3D printing. and that's the motor piece, the carriage piece, the idler. They have complex functions that you need to accommodate in that, and that's very convenient using 3D printing, because printing is good at that. You can get complex geometries, not necessarily so much strength, because plastic is between 5 and 10,000 psi, compared to steel, which is 50,000 psi and up. But it's still like 1/5 the strength of steel. I mean, that's not bad. It's better than wood. And so let's go through what are the printed pieces, what you can print here. So we've got the three axis pieces, but if you want to go a little more fancy, you can also print the actual pulley that goes on a motor. The printers are capable of doing that. We're not doing that, and I guess we just didn't get there yet.
It is possible. They do wear out, though. I've tried it at home.
Okay.
The little set screws can become...
That's
worn.
production engineering and designing it. So, for example, if you're going to put a set screw, because you got to hold the pulley on, hold it to the shaft very tightly.
You have to do it just right.
You have to do it just right.
It's gone.
In some of my tests, I found that if I just make the hole of the pulley a little bit smaller, it just clamps onto the shaft itself.
It helps.
Yeah. So
Particularly if it's a cut shaft. Yeah.
Oh, cool.
So there might be some redesign needed. Maybe make that little flange where the set screw goes, and maybe make it a little wider. And definitely print probably at 100%. Typically you print at 20% of the infill. You can control the amount of fill you have in any 3D print. You can do basically like a zigzag pattern inside like a honeycomb, or you can make it absolutely solid. So here, for a part like that, there's quite a bit of torque on that little pulley. So redesign it perhaps. The first step I would take is make a larger screw. Like the screws that are in there, like I think are 3 millimeter or so. Make it like 4 or 5, so that you have more plastic meat around it to hold it better, so it doesn't wear out. 3D printable. We have 3D printed the actual bearings, linear bearings. That's doable. It will have a little bit more friction than your ball bearings that are the metal ones. But if you notice, the current ones that we're building, they're actually the plastic, glide plastic material. And you can actually get that material off the shelf as 3D printing filament. So they're called IGUS bearings, that's the brand. So some of them that we're doing, we've used both the metal ones and the plastic ones, but you can get the 3D printing filament for those plastic ones to have that same kind of low friction. So that's really good. Next, what other things can you print? So we can definitely print the pegs. The pegs are the mechanism that bind the belt into place, so that you're not using like some kind of a screw or other things. Like thinking about this lowest part count, the belt I think allows you to both tension it. There's a little mechanism for doing that, but allows you to tension and hold the belt in place in one function. So it's like one part, or you can call it two parts that do that function. Otherwise you might have a more complicated system where you have to kind of like wind the belt around something, but this we're kind of proud of because that's like the simplest thing you can do, and it works really well. Okay, so what are some of the other features? Okay, end stop holder, 3D printed also. The end stop holder that we're using right now, it clamps right on the rods, and that you can
What an end stop is.
yeah, so an end stop is a little device. You put an electronic component on it that when you hit the end stop, it's got a little lever on it. It detects the limit of motion. Basically, it's connected to the controller, and it says, "Oh, okay, I've reached the end of motion. I'm going to stop there." So the machine can basically orient itself as far as where it is, because the machine by itself doesn't know anything without feedback. The end stop is one element of feedback that allows it to know that, okay, now the carriage hit the end stop. It's going to stop. It's going to know that's like the 0 point or whatever you set it to. Let's talk about the axis carriage, the motor piece. What are the functions required there? 1, you got to attach the motor. 2, you want to attach the motor piece to something else like a frame. And 3, you need a place where the motor shaft and the pulley goes through, so that the belt can be swung around it. So that geometry is basically built into those motor pieces. And the other element about the motor is that you have interior nut catchers. You see these two nuts on. Let me just go up so we're matching. Okay, so you see these two nuts that go into both the motor piece and actually the idler piece. Those two nuts go into a shape that holds the nut in place, so you can screw a bolt into that in order to be able to take the motor piece or idler piece and attach something else through the bolt holes of another piece. You can do it like that or like that. So it's an attachment mechanism. Right now, in the current version of D3DV 19.06, we are not using the nut catchers. We don't have to because of the way the geometry works. We're actually using these other angle brackets in order to expand the available travel area of the axis. But in the former versions and in other versions, if you need to, you can attach one axis at a right angle to another carriage piece as you need to. So you can mount an axis either flat against the surface through the bolt holes that go through the 3D printed pieces, or you can attach them through the end pieces with bolts that go into the ends. And if you look at the pieces, if you examine that more carefully in the workshop, you'll see that in more detail. But that feature allows you a flexibility of connection that allows different geometries to be made. Like, for example, in the absolute simplest variation of the 3D printer, you can have one bed that moves back and forth, then you can have a vertical axis, and then a third axis, like this or like that, attached to it through those nut catchers. Or you can lay it like that with the through bolt holes. So you have variations like this or like that you can do. But the idea is we've got bolt holes which can attach to other things. So you can attach things like whatever tool heads you have to the carriage piece. And for the end pieces, which are the idler and the motor piece, you can attach that to a frame, flat against the frame. Or you can attach it between the carriages of another axis. So there's flexibility there, which allows you many, many different geometries. Like, William, if you want to scroll down to some of the different geometries. So far we've built just the 3D printer, the very simple 3D printer, and go up to the circuit mill. So that's like this, for example. That's what the geometry of a CNC circuit mill that we used. So we had two y-axes. I mean, you can use one, you can use two. It's not showing up on my video here. Both y-axes. In this case, we've got two x-axes. Why? In that case, we have a spindle that touches the actually mills for a little circuit mill. A CNC circuit mill is a device that can etch. If you've got a copper-clad board, you can mill out a complex circuit pattern, or you can mill light aluminum with that. So it has force. So in that case, we wanted to do two of the x-axes to get you double the strength. So you're really containing that. The spindle would go inside there to contain it pretty strongly. And then you would have in the case of the circuit mill, instead of the bed, like in a 3D printer going up and down, you had the z-axis mounted on the carriage of the x. Let's see, can we pull up a picture of where this is shown better?
Is there another one in the
Go into
Facebook? Yeah.
No? No? Okay, go back. No, that's not it.
Okay.
So, yeah. But in real life, this is a good picture to look at. That's what you've seen. You're kind of getting familiar with that. Motor piece. So what are some of the critical quality control points here? One is you got to start with that the pulley on a motor is attached tightly. If you don't do that, you're going to have the pulley spin and you think, oh, the motor's not working. the shaft will just spin inside the motor. But there's 2 set screws. They're like about, I think, 60 degrees away from each other. And that's a configuration that you like to use. You don't want to do them actually opposite one another. That's the way set screws work. You kind of want to have them, I think 60 is the best angle, so that they hold the most tightly. But there's 2 set screws, and there's a tiny little wrench that does that. But you have to get it tight on there, otherwise it will spin. So you definitely want to do that. When you build the axes, just make sure that all the axis pieces, they are pretty clean of any extra plastic where the rods go in. So make sure that especially on the carriage side, there is no interference, like where the holes for the bearings are, that the rod just goes smoothly in and out. So in the axes that you're working with, just make sure that that is clear. Otherwise, the axis will be, the carriage would be a little tight. Now, how do you tighten the belt? There's a video on the wiki. I guess William, can you search if it's on the wiki? But that's like the only tricky part, maybe non-intuitive, of how you assemble the axis together. So what you do, the concept is that the belt pegs that hold the axis together, that hold the belt in place, they have a hole in them. So on one side, you're threading the belt through that hole, and then you're catching the other belt side. It's not easy to explain, so let's take a look at a video. But the general concept is that would not work unless the pegs were hollow. They're not a solid peg. They got a hole inside through which you thread the other belt, because when it's threaded, before you put in the other side fixing peg, you can pull that belt in order to tension it. So the tensioning mechanism is allowed by the hollow nature of the hole. And we can send a link maybe afterwards, after this, because it's on there. I know Shane did a video. Shane is the guy who did the CNC circuit mill. He put a video up of how you tighten the belt, but I can show that in a workshop, and maybe we can videotape that for everybody's reference. A nice little quick video on that would be a good instructional. We have one. I think we have some good cameras here. We should take advantage of them to do them. Okay, William, maybe go back. Yeah. Let's just go back. So this is 5/16 or 8 millimeter. In the case of the OSE printer, we've used both 5/16 rods, which are about 7.92 millimeters. They're almost 8 millimeters. They will work still. There's slight little play in there, like very, very slight, but it does still work. So for the metric guys, you can easily get 8 millimeter rods in Europe. In America here, they're actually a little harder to get, and there's more access to, if I'm looking for chrome rods, for example, from McMaster Carr, which is a good supplier for us. It's got everything. They have more in the 5/16 than 8 millimeter. So it's just differences in sourcing, but the only thing you have to pay attention there, you can use both 5/16 and 8 millimeter in the current system. So let's go to the 1-inch universal axis, and then let's go to the 2. William, can you pull up the 1-inch? So if you go at the very top, click on the 1-inch universal axis. There's a wiki page on that. So now let's scale this up and make it larger. So here you now see 1-inch axis, solid shaft, as just 1-inch cold rolled steel. And in one case we actually use these plastic 3D printed bearings. They're larger, they've got more resistance, they do work. But in the torch table that we built last year, 2 years ago was it, we used metal bushings, which are easy to source from McMaster Carr, as opposed to ball bearings. You start to get a little bit expensive once you start into the linear ball bearings at the 1-inch level.
What's a bushing?
Yeah, so it's an oil-impregnated brass bushing that we should have the BOM on this page. No, we don't? Yeah, there is. So the bushing is one of the most critical items here. This is on McMaster car. It's an easy gliding. It's, wow. See, the price just shot up through the roof right now. It's $4.75 each right now. It used to be about $2 last year. So this is the China embargo, it seems like.
Oh no.
I found that video. I emailed it to both of you.
Okay. You want to take a look at let's look at the belt tightening video, maybe real quick, because that is a critical component here. But essentially, once you kind of understand the theory of that, it's very quick. You just press the pegs in and they're a friction fit. And the belt is actually capturing, there's two belt holes. One is smooth, the other one is ribbed. The smaller belt hole is the one where you put the belt pegs. The other hole will be too large. The belt pegs will be very loose.
It might.
Okay. So the concept is, we got the. Oh, maybe lower. I'll just speak over that.
Okay.
So you're pulling one belt through all the way. Put it around the peg. Now the belt peg handle is facing towards the rods. Let me see. Maybe I'll on the Jitsi Meet here. I'll stop sharing my screen and turn on the video, which is more interesting. Yeah, there we go. So you guys can take a look at that on a remote. Well, actually, I'm capturing that on the video, so probably best for the remote people is to capture after it's posted online. The basic idea is, so you push the belt all the way through. You can push the belt peg in. That belt will be loose there. It slides in and out of the hole. Okay, but now you can simply tension it by using pliers, and then just put the other peg on the other side, and that's it. So if you can remember that, and then you can kind of strum the belt, and it'll be like a guitar. But the thing is, like with the pliers, you can easily rip that belt. You can get it super tight. Just do it very gently, so that you're just tight enough, and then you're putting the belt peg on the other side, and that's it. So no complex mechanism. It's just a through hole, which allows you this. Just make sure the belt, the angles are facing towards the rods, not towards the inside, because that wouldn't work so well.
Question? Did you find that this tension holds in time, or does it loosen and you got to retighten it, or is it?
When done properly, it does not come out. So this is a pretty robust mechanism. It's good.
It might be worth noting that there's teeth in the top space of plastic.
Exactly. When you see the belt, it's got teeth pointing up, so the upper side of that hole will have a corresponding ribbed pattern, so that there's more holes. So essentially, you got your teeth going into its hole, so that's not coming out. It does not untension.
I noticed that all the teeth in the 3D printed piece, it goes all the way across. Do you need that, or is that just easy to manufacture?
There's another detail in there, in that the belt peg holes are tapered, and they go all the way through. They don't have to go.
I'm just curious.
Well, the hole has to go all the way through because the belt obviously goes there, but the ribs don't really need to go all the way. But it's convenient because, say, you want to use a longer belt peg, you have more grip if you want that. But what else to say about that? The peg and the peg hole are tapered so that the farther you push it in, the harder it grips. So that's part of the design. Okay, let's go back to the 1-inch axis just to go over briefly on that. We've modified, so we're not just scaling when you talk about scalability, you don't just take something and enlarge it absolutely exactly. Part of scalability is the understanding that, okay, well, you might want to redesign some things in order to make it more efficient. So if you scroll down a little bit, for example, look at this is the motor piece. It's not exactly what the 5/16, let's call it 8mm universal axis looks like. So we made some changes on it. Like, for example, We cut off a little bit of meat off the end because you only need so much of it to hold the rods in place. And because these things now are getting pretty large, that's convenient, so the printing time is much less. We added 3 holes for the nut catchers so you can make the attachment to something else from the side. Before we had 2, so this is bigger, heavier, you want to have more hold on it. We added another feature where you still have the standard small NEMA 17 motor bolt holes, but if you've got a bigger machine, you want to use bigger motors, so we added another bolt pattern for the next size up motor, which is NEMA 23, so that you have much more torque on that. So this can accommodate either the tiny motor, because you can still use it, like if you don't need a lot of torque, you can well use that. If you need more power, use a bigger motor, depending on what you're doing. If you're doing a non-contact thing, such as a torch table, even the tiny motor will work, and that's what we did a couple of years ago. If you're doing a CNC router, for example, that's contact machining. You need some force to move it, so you might want to use a bigger motor in that case. And the stepper motors come in different lengths. So the tiny one is going to be maybe less torque, the longer ones are going to be higher and higher torque. So it essentially goes to the point where the most powerful smaller motor is the least powerful next size up motor, just about there. But you can get them to be like, tiny little pancake style versus like just as long as you want. There's no limit to actually how long you can make them, because the geometry in there can be scaled lengthwise. So some features we're basically modifying the pattern. What we are leaving here as details is the bolt pattern is interchangeable or compatible with the 8 millimeter axis. So you can mount this piece to another piece of the 1-inch axis through this bolt pattern that exists here. So these are the 6 millimeter bolts that you can attach other pieces to. Or you can attach the smaller axis, because the smaller size here, like the distance between those two and those two, that matches the 8 millimeter of the smaller version. So the two sizes are interchangeable. Now we haven't designed a 2-inch axis yet, but when we do that with the big rods, then we might want to make it compatible with this bolt pattern too, or maybe not. Because in a very big version, I think we want to go to larger holes. When you talk about, if you have seen the shafts that are under the table in the workshop, they are heavy. So we probably want to get away from the 1/4-inch bolts and go to another very convenient common size of 1/2 inch. Because first of all, the thing's going to be so huge, you're going to need that. And if we're talking about hundreds of pounds of force on the actual motion, yeah, you probably need more than like 1/4-inch bolts, though they might suffice. But the bigger thing about the 1/4-inch bolts, they're going to be fine because their strength is like a couple of thousand pounds that they could hold. Bolts, clamping strength of bolts is pretty insane. Like a 1/2-inch bolt, when you clamp down on it, or if you try to shear it, that is several thousand pounds that you can hold with just like a 1/2-inch bolt. 1/4-inch is a few hundred, maybe low thousands. So this year here, we could use 1/4-inch bolts for the next size up, but that would eat away at the plastic. Like the plastic now is the missing link. It's the weaker part. So if you have 1/4-inch that you're really clamping down hard with like 1,000 pounds, you're going to start deforming the plastic. So you want to have larger bolts, so the force of the bolt on the 3D printed pieces is lower. So I want to go through another concept of the plastic metal composite. For the 1-inch axis that we did last year, we took advantage of combining metal with plastic. So plastic easily generates very complex shapes that are usable for many, many things, but it does not have the strength, so that's the limit. But you can combine a very simple idea of using plate to reinforce a plastic object to make it much more industrial grade. So think, for example, about a 3D printed vise. right? By itself, if you clamp down on it, you'd eat it away. The plastic would eat it away. So put some metal on it. Put some nut catchers in there. Put a big 1-inch nut and a 1-inch bolt in there for the crank, so that the force is spread not on the plastic but on the metal, like the metal nuts. Make the jaws of it. Put a metal plate on the jaws, so that you're using the flexibility of plastic geometry with the strength of metal. And so, for example, with a 1-inch axis, when we built the torch table last year, in order to hold, we built a huge one. It was too big, 5 by 10 feet. But we had to have a little bit of reinforcement to hold the long the 5-foot x-axis. I think it was 6 feet even. And in that case, we used the metal plates around the sandwich. So let's see, go to D3D CNC torch table on the wiki. Where else? So we call D3D the Universal Access System, and the D in D3D stands for distributive, as part of our core philosophy of distributive enterprise. So that's a side on the name of D3D. If you go to the D3D CNC torch table, you can see how we use metal plates. So scroll down a little bit to some of the pictures. That's it. So that's the universal axis. But now you're reinforcing it to hold massive amounts of strength while using 1/4-inch bolts to do that. So these are like solid metal shafts. That works to combine, like the complex geometry. You want the belt peg holes, for example. That's a perfect example. The belt peg hole, if you're going to use that mechanism of using a little peg, it would be a horror, a nightmare, to try to mill out the 2 mm profile of the belt peg hole if you were to do it in metal. So use plastic. You've got the 3D printer. You get the ability to make complex geometries and then combine metal elsewhere. So basically, if you take a look at any appliance and many tools out there, it's like, if you break it down to very simple components, it's like you got plastic and metal. Screwdriver, you got a plastic handle, metal blade. You got a microwave. It's a bunch of plastic parts, and then maybe metal casing. That's not a great example, but say take a look at a washer. You can say 3D print. You can say 3D print the blades, the complex geometries inside out of some solid ABS, solid, and then you've got metal frames around it to hold it all, like hold the motor. So just think about the concept of the power when you mix the metal with the plastic. And for the metal, here you can do digital fabrication on both the metal and the plastic. So you don't want to be doing those holes in there exactly by hand, because you got to measure everything. And actually, when it comes to build, measuring is actually longer than drilling. You got to know where to drill the holes. To drill a hole is a few seconds, but to locate that hole is harder. So that's the advantage of a CNC torch, which we agree on. You can cut out the plate, put it on the torch table, let it do all the geometry for you, and you've got access to advanced equipment, very low cost, because plastic is, right now, if you buy it off the shelf, it's about $10 a pound. That's doable, but it's expensive, so that's where the filament making infrastructure comes in. Then you can get plastic for like 20 cents a pound, which is the electricity cost required to melt plastic and shred it. So you're talking about, once we get like to the larger axes, and like if we're going to produce that, man, if you were to print those 2-inch pieces, I did some samples that I just put it into Cura, the slicer, for a 3D printer. I looked at, okay, how much material am I going to use if I'm going to do 100%? Because, yeah, we want to use 100% infill when we're using those heavy 2-inch axes. Well, it takes about 1 spool, like 3/4 of a spool, or up to 1 spool to print just like 1 piece. So that would get pretty expensive. So you're talking about $20 per piece. If you got 6 axes, you got 18 pieces. So 36, because it's double clamshell, and each one is pretty heavy. So the point is, like, when you're designing and building this, you have to take a look at your costs involved as well. If you're going to be printing large things, yeah, you got to start paying attention. Like if you're going to be printing furniture or anything else that's heavy, anything like tables, chairs, your refrigerator bodies, and whatever, skateboards, you're going to have to look at the weight, and it becomes feasible. Construction materials like plastic lumber or plumbing, all doable, but you get into away from this is 3D printing to this is materials processing. Talking about then getting 1,000-pound bales of trash and throwing them in a big grinder if you're going to do that economically efficiently and like village scale. But I think you can do a small business with a small grinder. You know, you recycle plastic from various sources. But at the next level, where you want to do like as efficient as it gets into just massive materials handling. If you're going to be making 3D printing filament for sale, for example, 2,000 pounds of big bale, I mean, that's 100 rolls of that, of filament. 100 times, no, that's 1,000 rolls. Well, but the numbers add up in terms of heaviness. For the torch table, just as an example, if we're using plastic off the shelf, $10 a pound, we're talking about 36 pieces, and each piece is going to weigh about a pound or two. They're going to be big, like if you talk about 2-inch axes. So 36 times 20, $720 just in plastic. Man, that gets heavy. You want to get that down to a few dollars, $10, $20, to make the larger machines truly accessible. Because I mentioned what's the line? What's our vision? Does anyone remember? What's the vision of OSE? Can someone read it? I want to hear it again.
Lifestyle engineering course. Oh, I'm sorry, no, that's...
No.
Collaborative design for a transparent and exclusive economy of abundance.
Exclusive, no.
Inclusive.
Okay. So let's take a look at that statement.
Share with everyone, except John.
Collaborative design for a transparent and inclusive economy of abundance. If we take a look at the word inclusive, that means production for everybody, no barriers. Inclusive implies that we're making the filament. We cannot afford $720 for a heavy-duty mill like that because there's going to be much other costs. So bring it down to make it inclusive, make it accessible to everybody. So it's not just something that someone with capital can do, but someone who can bootstrap from nothing. You've got the ideas, you've got the tools, you can bootstrap. Ideally, the situation is that you've got microfactories all around that you can subscribe to at low cost. Maybe whatever, like a hackerspace these days, membership might be like $50 a month or whatever. So whatever the microfactory membership model is, for that amount of money, you can bring in your trash, and if that microfactory is equipped with your filament making infrastructure, you're doing that at the cost of electricity, which is going to be about 20 cents a pound or less. And if you go in solar, it's less than that. So with PV, that's using off-the-shelf photovoltaics, which today are hovering around 40 cents a watt. I mean, if you understand that number, that translates to about 2 to 4 cent electricity cost, as low as 1.5. At our house, our cost of electricity is 1.5 cents per kilowatt hour at the CDECA home, using the DIY photovoltaic system that we put in. But that's a game changer. If you have access to low-cost electricity, all this becomes feasible. We talked about the sun providing 10,000 times more power than we use in the entire civilization. So that's an abundant resource that can take us there. So that's a brief overview of the universal axis, and we can continue to actually explore it in real life. What you can do to get more familiar with it is there are part libraries on the wiki. So if you go to the universal axis page or a 3D printer part library page on the wiki, you can download all the individual files and manipulate them and view them in FreeCAD. so that you can examine what they look like. Or you can take the STLs that we have online, you can throw them into Cura, which is the 3D printing software, and you can start looking at, okay, how much print time does it take for different scenarios? Like if you printed, standard is 20% infill printing, how much time and energy does it take to print at 20% versus 100%, so you can kind of start getting a feeling for, if you're going to be doing real product design, you have to start looking at costs. Like what is the exact cost of, how much does it take to produce it? Say you want to be making, you set up your printer cluster, you just want to produce plumbing fittings, say it's a fully automated process, you can actually beat Menards in terms of the costs if set up properly. So, but you cannot do it if you use off-the-shelf filament unless you're doing high-value parts. But you can even do the low-value stuff that you find at Menards if you are making your own filament. So the case here is that, wow, we can distribute production massively. Now there are very serious challenges to that, but I think they're being overcome as time goes on. And that is excellent designs, open source production engineering. There's the quality control, that's a huge, huge thing. How do you get that part to meet all the specs? Big one. And we're going to have to address that in the cordless drill challenge of next year, because if we're going to have 50 to 100 people producing, you cannot have that they have all types of variations and features between the different versions. It has to be meet or exceed industry standards, meaning they have to be identical. So as a start, everyone will have to use the same production equipment, which means open source equipment that we settle on. This is a version that we use and we go with it. And part of the we were building the universal access yesterday. My shortcoming on that was that we keep changing stuff. So this is up to the latest version, and I gotta make a decision somewhere, because it's like we added a few features, but every time you do that, the minor variations, like in a setting like right now, you saw how complicated it was to, or maybe it wasn't as transparent as it could be, because there were, even in what we were building, we had some options like using the spacer or not, like
moving target.
Moving target is a hard thing, and we need to settle on a version which is going to be absolutely critical for both replicating workshops like this and getting production out there. So that's a thing that we have to do a freeze somewhere, because what we have is good enough. But just to tell you, the freeze, the only thing that makes me uncomfortable is, once again, inclusive economy of abundance. We cannot do the freeze, in my opinion, I was kind of like chewing this last night, we cannot do that if the advanced extruder that does the fast and furious printing and high quality printing, meaning right now the off-shelf version that does that is the Titan Aero with, they have the super volcano nozzle. That gets you to even doing construction materials, because the extrusion rate there is 20 pounds of plastic per day. That's like 10 rolls of plastic per day. That's the super volcano nozzle heater block on the E3D extruder, which is what we're using. But the only trouble is that that package costs $250. That's as much as a 3D printer, a low-cost 3D printer. So that's kind of like the challenge. Maybe you can help here, but we want to design the open source extruder, which we started on, but one that does 3 millimeter and has the very big heater block, and not only that, but a scalable heater block. The big ones, the largest one you can get off the shelf right now is 80 watts, and that's the Super Volcano, and that's what allows you to get 20 pounds per day of printing. So you can print out a few 2x4s in a day. That's good. That gets you into business from the trash stream. Doable, but the only trouble is, so that, let's talk about that little heater block which I mentioned. So the heater block is about 2 inches long. It's a piece of aluminum with threading and some other little holes in there and slightly machined. But you're taking a 25-cent block of aluminum and you're charging $100 for it, because it's got some machining. And the way it works is that Not a lot of people use this super volcano because not a lot of people are into any kind of serious production as opposed to just hobby stuff. Therefore, that super volcano nozzle is super expensive. To the point of 25-cent piece of metal costing $100. And that's a common thing. You machine something, you make it, add value, add information to raw matter, and you charge a lot of money for it. Well, if we have the open source information, then we're taking it down from a 25-cent block to something you put on your CNC circuit mill or mill in general that's open source, and you create $100 value with 30 minutes of machining. That's good. That makes sense. So, I mean, that's the kind of stuff we got to get to, and once again, it's why we're doing the STEAM camps and trying to spread this so we can teach people about all of this and have people do the thousands of these problems that are of economic significant value that can be done using open source technology. So let's leave it at that. So we'll pretty much wrap up the remote session. You guys can still hang on, but we're going to talk here. Maybe any questions on the universal access system? Anyone in the crew here? Or remotely?
I always ask questions. So, one of the things that I noticed and a couple of us noticed yesterday, I think, is the tolerances of the plastic and the nuts and bolts. Like when you slide in the bolt and the nut, and sometimes when you tighten it, it will literally
flatten it.
No, just spin inside of the little cutout for the nut.
The nut retainer.
The little nut
strip
pocket.
Okay, so
You mean it's stripped out?
if it strips out, it's probably, you have to pay attention to the setting on a. Is that manual or with the cordless?
No, that's just manual.
Manual?
Okay. Then at some point, I don't know. It might be that you just need sensitive attention. And,
you can do it with all your ports.
Right,
Don't overdo it. So if you did overdo
it
it,
just felt too easy.
okay. So, and that's another thing. So those are all printed at 20% infill, so they're not like solid at all.
Well,
If you,
there was also a little bit of open space around the bolts in the retainer slot.
so that may be a thing that we might have to pay attention to. We never really ran into this problem, but that's the kind of variations in quality control we need to really nail out. Because as we're moving forward and the moving target thing, maybe like things change slightly. So we really got to once again maybe get that to the finish line. Yeah, we haven't had that issue really before, but if that's a persistent one, pay attention to that and see what we can do. Okay, so we have a question. First of all, there will be another remote session this afternoon at 2, so we're going to really try to stick to the schedule at 9 and 2. That's what we're promising, and otherwise, can't guarantee anything. So that's definitely happening, and we'll tackle a little bit of collaborative literacy after that. We have another question here. What's the estimated cost of the parts of the universal axis for a medium-sized build? The axis is, what is it, like $25 an axis for the universal axis? I can break it down. The most expensive part is the motor, which is $8. You can get those. The rods are, I forget what they are, but it's the plastic pieces. It's as much as it costs you to 3D print them. If you have your own 3D printer, that's 50 cents or $1. There's the bolts, which are like 15 cents each. There's the belt, which is under $1. There's the idler bearings. They're about 60 cents each, so $1.20 there. There's 4 bearings. The bearings are about $1 each, so it's $4 in the bearings, but it all adds up to about 25 or so. And if you're printing any of those parts, you'd take out those costs. For the idler bearing, for example, it's feasible that you 3D print that and let that spin around a flat shaft. So we haven't done that, but that's a doable thing. So you can really try to push the limits. Now we're using easy to source off-the-shelf parts, and they're proven, they're well worked out. But if you do make any of these changes, such as using 3D printed bearings, idlers, or pulleys, okay, then you need to know what you're doing, and it's harder. But once open sourced in the production engineering level and quality control, that becomes replicable. So that means publishing all the settings files that you're using to 3D print them, publishing all that surrounding production information that's necessary. It's not just you have a file and you just print it. There's knowledge and settings, what printer you're using, and so forth. Materials choices that are relevant. Okay, another question. From a cost standpoint, what about 3D printing molds and casting from aluminum into them? A good propane-powered metal casting furnace is cheap to build, about $300 to purchase. Exactly. So that's one of the great uses of 3D printing. If you do print 3D printed molds, you're not going to cast into a 3D printed mold because that will melt out, but you print a 3D printed mold and put that into, for example, plaster of Paris for aluminum. Plaster of Paris is dirt cheap, so you print a complex part, you print it out of PLA. They actually have other materials that are more dedicated for 3D printing, but then you just burn that out, or actually pour directly into that if you have a proper design, and it burns out and leaves just the metal. So there's a very direct link from 3D printing to metal, especially if you could. Now, what about steel? If you can melt steel, yes, you have to have some information about the refractory material, because plaster of Paris will not do. Steel, you're talking about 1500 Celsius. But that is a great use case if we can open source the refractory material and the whole process around that. That is just huge value right there. That's one of the thousands of extremely valuable. That's a multi-billion-dollar project in terms of value. Well doable in distributed production. Someone has to do it. And develop the open source induction furnace is in the GVCS, the Global Village Construction Set, so we're all set for that in the future. Right now we can't do that, but we'd love to cast, for example, at that point you can do much more accurate casting of things like sprockets or even gears. If you do gears, you'd have to probably post-machine it to a very fine finish, because gears are typically finished with grinding to get a super precise surface on them. But yes, direct link to metal through the plastic by using that as molds. Great use case. Yeah. And they comment is cowboy casting builds a 300 plus furnace that can melt steel. Yeah. Once again, that's almost doable with an electric, low cost electric furnace. You can do that for not for steel but for cast iron, which melts actually around 1200 Celsius. So using very inexpensive nichrome or canthal. Canthal is another form of nichrome heat wire. Using canthal wire and the techniques we will do today when we build the open source heat bed, we're going to learn how to take nichrome wire and make a heater element out of it. That identical technology can get you to that metal melting, the actual cast iron melting furnace, and very easy to do that for aluminum. Aluminum is lower melting, but yeah, great connections. And the product ecology, once I was doing the heated bed that's DIY with the nichrome wire, yes, absolutely all the, like the furnaces, kilns for pottery, metal melting furnaces, heater elements, toaster ovens, and all that. That all comes right out of that kind of technology. So once again, reinforcing the idea that there's some very basic primitive technology elements that are used in many applications. So if you have a basic idea of the building blocks, you can really go to town in a construction set approach. So that's the idea. Any other questions? Okay, please talk about 3D printer PCB controller. What controller is used? Arduino, and what motor controllers chips are used, please? Okay, that's the universal controller. The universal controller that controls the 3D printer can be used identically, but with different software, for the CNC circuit mill. It's Arduino based. It's got the Arduino Mega with like 50 input-output pins. It's like, what is it, like 32 megahertz, is it? It's a processor that, if you know how to use it well, you can get up to applications like laser cutters, which move, or laser engravers. So the answer to that question is the universal controller, which is the same one essentially that we're using for the 3D printer. So we've got that as a package that's applicable to not only the CNC machines, but also to the brick presses and any other automated equipment that we want to build. The motor controller chips that we use, so we use the ramps board. It's called the little shield that we use on top of the Arduino. It's called ramps. It's called RepRap Arduino Mega Pololu Shield. That's the abbreviation for that. It uses these tiny stepper drivers, which are A4998, or these other Pololu drivers. You can Google Pololu stepper drivers. Tiny little chips, cost like $1 each or less than $1 each. You can get those same chips that are in the last couple of years, they came out with ones that are absolutely silent, and ones, because typically 3D printers make a lot of noise, and these machines can make a bunch of whining noises when they run, but they made ones that are completely silent, and ones that can detect when the current goes higher. In other words, if you hit a limit, like say you hit the actual end, in that case you don't need an end stop, because the chip actually detects when you have hit and caused higher current. It reads that higher current and says, oh, I reached the end, so no end stops needed. That's one of the other iterations we can do for the 3D printer. That's useful because you're removing two physical elements, the end stops. Now with the universal controller, like what controllers do we use? Yes, those are the plug-in simple Pololu style steppers, but you can plug in any external driver. So using 3 pins out of that connection, you just wire that up to a stepper driver of any size, so you can run a machine as big as you like, any size. So the system is designed for either the internal built-in, the snap-in small stepper drivers, Pololu style stepper drivers, or external ones, and I'll be talking more about that with the universal controller session, so we can maybe save it for there. How close is the universal controller to being built by the Open Circuit Institute circuit mill? It's doable right now. Someone's got to do it. We can mill complete Arduino. We can mill the stepper drivers. You have to redesign it a little bit to make it feasible. On the Arduino, there's a tiny chip, and there's different variations of that chip. We have to redesign it just slightly, but if someone can do that in their ample spare time, great project. The CNC circuit mill right now has the capacity to do 0.5 millimeter traces. This is professional grade. So you can look at the paper. If you Google on the wiki, go to the D3D CNC circuit mill, you can look at its specs, and there's a link to the paper on that. That is ready to be taken to town. Once again, multiple numbers of things that can be taken to replicable grade. Do we do SMD for mounting or drilled through holes? Surface mount components. You can mill with a circuit mill. You can mount circuit mount components to that. There's components that don't have like through hole wires. Some are just like surface mounted. You can mount those. Now the circuits we did before with a circuit mill, they were through hole for standard components, but you can do both. The limit is that you're limited to 2 sides. Like if you take a copper board, you can mill on one side. You can also mill the other side, but you have to flip it, and so that's manual work unless you automate that. That's the current status. Should we make a CNC soldering device for the above? Yeah, I think the nichrome heater element gets you directly to that technology. Can you design it? Thank you. Okay. After the 18 lessons, you'll be probably able to design it. So it's a challenge for you. Whoever asked it, that's Eric. Okay. JPNP, what software is used for circuit design that the CNC circuit mill uses? KiCad. So KiCad is a powerful open source package that you can do any kind of design in. It's competitive with EagleCAD. You can do just about anything in it. interconnection to FreeCAD, so you can export KiCad, K-I-C-A-D. Great piece of software, professional grade. Now, in this whole search, you did hear me talk a little bit about computer chips, that we can make them on our 30-acre farm. Well, they do have components of that already, and that is open source chip design software is already out there. People, all the capacity is out there. It's a GPL license, it's fully open source, it's actually managed by the Free Software Foundation for them. I forget the names of it, but there's a couple of them. Circuit design like chip design software, like the real complex stuff. Now, no open source equipment exists that can manufacture it, so that'll have to be later. But you can take those designs and take them directly to an outsourced fab, semiconductor fab shop, like in Taiwan or wherever.
On the edge of that, I've heard of a kid in high school who, through eBay and through a couple of contacts, managed to get a hold of like high vacuum chambers and electron scanning microscope stuff, and has managed to make like very simple chips.
Yes, yes, that's exactly right.
So it might be gradually getting there.
yeah, it's all getting there. It's just a matter of time, and it's getting easier and easier. Okay, so any other questions here on Universal Access? Everything absolutely clear for today? Okay, so what I wanted to cover, to wrap up on the Universal Access, what are the learnings from yesterday? Okay, how do we make that easier? We got to 2 axes almost. Nobody's mounted the axes yet. We wanted to spend the morning just doing that, and then moving on to the electronics in the afternoon. But can we record some learnings from that? Aiden.
Self-tensioning is difficult. The video is now on the CNC Access page, the Universal Access page. So if you need to watch that video, just go back to that webpage and it'll be there.
Excellent. It's a good start.
One thing that I noticed when you were assembling it, you had to flip it over a bunch, and that just may be part of the assembly process, but when you have to flip something, it just makes it more complicated to hold parts in place, to flip it over and have to put everything together. And I understand why, like, you know, to be able to take it apart and be able to access all the interior pieces, you kind of have to do that, but if there was a way to get around holding pieces on one side and then flipping it over to put everything together.
Well, if you can contribute to that, maybe throw down some ideas. What I would like to suggest for everybody is start a log. The most easy way for people to find each other is like Aiden log, Marcin log, William log. You can find those pages on the wiki. The wiki is wiki.opensourceecology.org/wiki. It's complicated. But Google OSE Wiki. Get an account and start a log. That's what. So, like for example, Michael, you're saying, hey, that's a good thing. Do it. And then, how do I know that you did it? Well, I'll remember that conversation. I'll associate it with you, and I'll look at your log. So, if you did it, I'm going to know it's there. Otherwise, you might put it on some page where nobody knows. But it's the easiest if you organize by name, because name is easy to find. So that's convenient. So do that. Now, for right now, working with what we have, what can we do? One thing I want to point out, and I know some people are taking notes, but absolutely take notes. Try to take notes, because I know I said things many times yesterday. Can we do that experiment? Does anybody take notes here? I see a few people, but I really like to take notes in my fat notebook. But do something where you can capture the information, because I'm telling you, like, we are so limited in our memory. Short-term memory is weak. You can remember one thing. You're guaranteed to get one thing. When it comes to 2 things, 3 things, forget about it. I mean, use the notebook if you can. So please go down there with a pen and paper, because we'll get farther faster. So
this is being recorded, and will this be available?
This all will be available. This is the lecture right now. I've been recording all of this with a screen capture using OBS Studio. So we do have all of this, so you can review that. And especially for the remote people, you can the video will actually be cover some of the dead spots if you want to go over that. Anything else on the learnings? Because the idea was for collaborative literacy is how do we work together and teach each other? So we're picking up the learning curve on this stuff. But what I would like to propose, we work as a team. So what we found throughout the years is that if we stop and the first person that's done is liberated to the step, and that's why I said do the first 2 axes, get there. That defines a breaking point. So at that point, the first person that does that helps everybody else, because otherwise we're not going to finish. That we've seen that over and over. So try this. We've gotten consistently better results when we attempt to, the first person finished, help others. That may not be easy. That's probably not how we think, but do that. But we really want to emphasize that.
Another point, I think.
Wait, before we run, could you say, we finish the whole thing, or just finish a particular set?
Very clear breakpoint. So I would say, so the main challenge right now is doing all the frames. So ideally, yeah, it's kind of, I'm not picturing the whole thing, but definitely the breakpoint will be frames are done. That means we got to drill those holes, and 2 axes mounted. That's our reorganizing point. We bring everybody up to the 2 frame, to the 2 axes, and quality control it, meaning that okay, we look at it, make sure there's nothing wrong with it. That's obvious. The carriage should slide back and forth easily. It should be relatively straight. You know, basically looking for tightness of motion, making sure that the motor is engaged. Like when you move the axes, you can see the shaft of the motor spin from the other end. Things like that. It's not tight. So basically tightness and straightness, which it's not like that. It's mounted straight and stuff like that.
There are a few points that might help. One thing I found in my STEM classes, there's a lot of specialization that goes on because we're accustomed to everyone having the same outcomes. So in this case, we have a problem, and so we have the frames. It turns out that the holes are not all the same holes that we need for the current set of axes and the current design. So there were a few people who were working on that yesterday. If they were to become specialists, maybe a few of the others who are working on the axes who have finished could help them finish their axes. That might ensure a consistent quality control, and it would allow us to maybe get a little bit of efficiency if we had someone just focusing on the frames and someone else helping to take up the slack with the axes. Mm-hmm. Another part is, I saw this yesterday, and one of the biggest things I've learned from OSC work is thinking ahead. Because as a kid, I was just like ready, fire, aim with pretty much everything. And with the D3D, when we did this a few months ago in November, and we put something together and we have to take it apart, and I thought, I saw a lot of people having to do that yesterday because, the bolt is a little bit different in this particular part. But there were a few of us yesterday who were really thinking ahead. And that will save a lot of time. So the key mode is not to hurry and be the first finished. It is to think clearly and organize things as much as possible and think step by step. It's a little slower to begin, but it will be much more effective in the end. So gaining that, the ability to foresee 2 or 3 steps ahead is really helpful in this work.
Right. And the thing to watch out for there, for the leader, is make sure you're not propagating an error. Because that's a common thing that can happen. There's the superstars that sometimes do that and say, okay, I got it. Make sure that you know that it's right. So either ask or look at the machine, like be confident, like be able to defend it that you did it, because you don't want to propagate the whole thing wrong to everybody else. So don't be scared by that. The simplest way to answer that is ask me or ask William. Or if it's obvious to you because you have experience, yes, run with it. But a lot of times don't assume you know something maybe, so it's a little challenging, but there's an easy solution, which is asking. Or just getting verification from 1 or 2 sides, something like that. So, anything else we can learn from yesterday?
This is something that's come up in my professional practice, is defining what the terminology that you use and defining that for everyone. And I think what I noticed yesterday was what is meant by a carriage component. Like you said, we needed 10 pieces. What's a piece? Yeah. Is that half the clamshell or is that a whole clamshell? And I think defining what, defining terms. Yes, exactly, defining terms. that communication, that connection, that's where these tend to break down. And so making it very apparent, that a very specific definition.
Yeah.
I think would help.
Yeah, glossary and a manual would be pretty good. Yeah.
Yeah. Yeah.
Is that something you want to start to create a glossary?
I was just talking. I mean, we were just kind of. I mean, a plan set would even be. I mean, I think even the 3D dimensional view that we saw today of the different pieces labeled, print it out, and just like one set on each thing so that we could reference it, or just a couple of them floating around would be a huge help.
I'd even take a step further and just do like the IKEA model, where you could literally just print out a part number right on the plastic piece.
Yeah.
Oh,
this
that's cool.
Is B,
Yeah.
This is C. Now you're not comparing and like
print it right into the plastic.
Yeah, we've been all day.
Yeah.
We're mounting something like, oh shoot, this is like, oh, this has 2 holes instead of 3, and now you gotta like take apart the whole thing, right? So having just like a label right on it, just print it, right? Just print it out.
And
you can do that
right now. That one is a prototype, so I didn't know if there actually were plans or not.
There's plans that don't have all the detail like bolts. Yeah.
I mean,
if people want to bring a computer into D3D v19.04. So yeah, if you bring your computers down there, you can download the FreeCAD file. You can just rotate it in the FreeCAD. Yeah.
That's perfect. Yeah.
Yeah. D3D v1904. Yep.
Did anyone bring a GoPro or any other? Because part of the documentation says writing it in the wiki, and writing it is just kind of capturing stuff. And I always have a time-lapse camera set up to show you this, so kind of captures the whole day from one angle. But if we have more, it's
that's
nice
cool.
to get closer shot. I'll each time
I have different angles in the same thing with
Okay.
time-lapse, so that would kind of...
Yeah, and at lunch I'll just HDMI this to the big screen and I'll kind of watch it where. But if anyone else brought any other cameras, I can set them up a little bit closer or right over a table. Then it's just then you can kind of see.
I think I have a couple.
Okay, so I'll get with you to figure out.
That. Anything else that comes to mind for people? Okay. No.
As far as setting the distance between the motor mount and the idler, you want to make sure that those bolts that are coming out are where the bolts mount to the bracket and the bracket mounts to the frame. You want to make sure that, because you're going to be tensioning your belt, and then your belt's going to prevent your so the idler end, as far as defining what that means, is where the bolt is, I mean the belt is just spinning on that little circular, we call it an idler pulley. So just watch out when you're tensioning your belt that you've already got your idler and your motor bolts set at about the right distance you need to mount to the frame. Does that make sense?
I think so, but we don't actually have a bolt pattern laid out for the frame yet.
Yeah, just
so it's going to be there's going to be a little bit of
look at the other ones. Take a look at the built one and just make sure you're close. I would say within half inch, maybe, just so that if you do make a small adjustment later with your either tensioning or detensioning your belt, and it's not too big of a deal.
I think at this point, just practicing doing a little tensioning is better. As we found yesterday, when we tension it and it's not mounted to the frame, it's just going to pull the pieces together on the rods. So just learning how to do it, and probably better to do how Marcin has been doing it. I invented a whole bunch of different ways of doing it.
Yeah, the idea is leave the final tensioning for later, because once it's on a frame, it's absolutely fixed, and you're not going to like pull it in. The final adjustment for the whole depends on the belt being loose, so you can adjust it in and out. It's self-adjusting at the end, and then you tighten the belt for the last time. For now, it's like all practice. Okay. You can just put them in easily.
The belt doesn't have to be tight.
No,
right now.
Not right now. Yeah. That's a good point. And we also seen just one thing to point out. You've seen that on mounting the Y to the frame. You saw the bolts that are used as spacers. That's because we didn't really have the spacers at that time, but we have plenty of those spacers right now. You can use the spacers, which are easier to get than screwing on a bolt, because you can just slip in the spacer just like that, and you don't have to worry about having that bolt on there. I know that on the other Y, there's like 1 or 2 nuts even. For us at this time, I think just 1 spacer will be fine. So just write that down. one spacer instead of the bolt spacers, because we're using the bolts as spacers right now.
I mean nuts.
Nuts.
If we were to use
Nuts.
nuts, is that okay?
It's okay. It's easier with a spacer. Mm-hmm. I can't think of anything else. Yep. Okay, let's hit the shop.
Oh,
Thanks, remote people.
actually, yeah.
Back to
One other
people.
thing.
Oh, I got some housekeeping, so don't go yet. I'm just gonna
This might be good to go through.
quit the OBS studio.